Welcome back to the Machine Learning 101 course. In today's lesson, we will cover multiple core machine learning concepts. First, a quick recap. Supervised learning is a type of machine learning where we feed the data with right answers. Linear regression is one example of supervised learning algorithm. If there's only one input feature, linear regression is a simple line equation, wx plus b. As part of model training, we need to figure out the values of w and b such that we can make accurate predictions on unseen data. Given that machine learning is all about finding patterns in training data, if our data is noisy, biased, or incorrect, our model quality will suffer because of that. We can use various data cleaning techniques to improve the quality of our data, resulting in better quality models. In this video, we will learn how does linear regression algorithm figure out the parameter values that best fit the training data.
As per our linear regression model, we need to fit a straight line to it with equation y equals a0 plus a1 x. And depending on values of a0 and a1, we can have many possibilities which look promising. We need to settle the case on a value of parameters a0 and a1 corresponding to which straight line fits best to the data. For this, we need to agree on a metric to judge best fit, and we can choose that straight line which performs best on that metric. First function to the rescue. Let's suppose we have m training examples or observations, and this is the first one. This is our model. From this, we know that this is actual price of first example, and this is price of first example as predicted by model, which falls on our straight line for that size. Let's call this difference as error term E, which is y actual minus y predicted. Since it is for first example, let's call it even. For ith example, we define error term as EI equals y predicted minus y actual. Now, as you might have understood, EI can be positive or negative depending on whether y actual is more or y predicted. We will square EIs to make it positive so the order doesn't matter. Cost function will be defined as 1 by 2m even square plus e2 square and so on till em square, where m is the number of examples and EIs are error terms. We can also write it as 1 by 2m summation of y predicted minus y actual square. We just expanded EIs y predicted minus y actual. We can also write it as 1 by 2m summation of a0 plus a1 x1 minus y actual square. We just expanded y predicted, which is a0 plus a1 x1 as per our model. Clearly, cost function j is a function of parameter space a0 and a1. I think you would have guessed it by now. The best fitting model would be the one which minimizes our error metric, which is cost function. Such a straight line will be the best linear approximation of the linear relationship between house price and size of the house. Another interpretation of cost function can be the measure of distance of our model from data points. Lesser the distance, better is our model. Now, we just need to minimize cost function, but how to do that? We have established the fact that all the straight lines are just different combination of model parameters a0 and a1. And cost function is a function of parameter space as well. Therefore, by changing a0 and a1, we can change the cost function. We will keep changing a0 and a1 till we find a combination where cost function is minimized. And for this, we will take help of gradient descent algorithm. Let's just forget cost function for some time. Assume a function, any regular function j equals f of a. This curve of j represents the values j will assume for different values of a. Indeed, that is what makes it a function of a. We are at this point now, a1 and f of a. And we want to reach here. We want to know for what value of a function will assume minimum. How can we reach minimum starting from a1? Let's calculate slope at this point, a1 f of a1. It is dj by dA at a1 or f dash a1. Don't worry if you don't understand dj by dA, you can interpret it as a slope at that point. Let's move a step alpha in that direction to reach a1 minus alpha times f dash a1. Alpha is a small fixed quantity in the range of 0.01. Therefore, the size of our steps is dependent on the slope f dash a1. Higher the value of slope, which occurs away from minima, larger the steps and vice versa. As we move closer to the minimum, the slope decreases and hence our steps toward minimum keeps on getting smaller. At minimum, slope becomes 0. These iteration of gradient descent algorithm can run in thousands or tens of thousands depending on nature of function, our learning rate, and of course where we start from, even in this case. We will use the same methodology to minimize cost function, which is a function of model parameters A0 and A1, by changing them through iteration of gradient descent algorithm.
As you might have guessed, the cost function of linear regression model is very similar to root mean square error. As we are not taking the square root here and dividing by 2, it is half mean square error, or MSE. The cost function j is a function of the model parameters. In the left diagram, all three lines are poor fit to the data. Hence, the cost j would be very high. In the right, the blue line is a good fit to the data. Hence, the cost function j would be low. When we plot the function j and b and w as the two dimensions, it looks like a hammock or a soup bowl. In order to find the minimum point, we simply need to start from any random point and keep walking down the slope. Let's say we pick some random values of b and w such that the cost is the blue dot. We calculate the value of the slope in each direction and update the values of b and w such that we start walking down the slope. We repeat this process until we reach the minimum. The resulting b and w are what we use to make all future predictions.
Problems are underfitting and overfitting. Underfitting usually occurs when your model hasn't had enough time or data to train with, and as a result, it cannot pick up on the general patterns needed to make accurate predictions. It can also be the result of a mismatched model, say, trying to fit a line to data that is in reality distributed along a quadratic. You can generally resolve this problem by picking a different model, increasing the amount of time or iterations the model trains for, or using more training data. While underfitting is quite straightforward, overfitting tends to be less intuitive. Overfitting essentially occurs when your model is too accurate. What this means in practice is that the model has learned patterns that are only in the training data, effectively using the random noise that arises in real-world samples to make predictions. This is obviously a problem because our new data will almost certainly not feature the patterns and noise our model uses, and, as a result, new predictions will be markedly less accurate. You can look for overfitting quite easily by comparing the error amounts between training data and validation data. Validation data being data you haven't used to train the model already. Here, you can see an example of the accuracy, mean absolute error, and mean squared error that might occur for an overfitting model. If you see that your results look highly accurate for your training data, but terrible for your validation data, then you are looking at overfitting.
In our first lesson, we trained a linear regression model that was clearly an underfit to the data, and hence the training and test error were very high. In case of overfitting, you will observe that the training error is very low, whereas the test error is very high. This is bad, as our objective is to learn the patterns from the training data, not memorize it.
Imagine we had this data and we wanted to use favorite color and height to predict if someone loves Troll 2, which is a movie that some people love and some people don't. In this case, favorite color has 3 discrete values: blue, red, and green. Now, in theory, discrete features, like favorite color, are fine for most machine learning algorithms. But in practice, a lot of popular machine learning algorithms, including neural networks, do not work well with them. As a result, discrete data are often converted into numerical values before being used for machine learning. One popular method for converting discrete variables or features into numbers is to use something called one-hot encoding. When we have 3 or more options for a discrete variable, and, in the case of favorite color, we have 3 options, we start by creating a new column for each option. In this case, that means creating 3 new columns, blue, red, and green. Now, in the blue column, we set the value to 1 if we had blue in the original favorite color column, and we set the remaining values to 0. Likewise, for the red column, we set the value to 1 the one time we had red in the original favorite color column, and we set the remaining values to 0. Lastly, for the green column, we set the value to 1 if we had green in the original favorite color column, and we set the remaining values to 0. Note, the last column, Loves Troll 2, is also discrete, but it only has 2 options, yes and no. So we simply replace yes with 1 and no with 0. And now all of the columns in our new dataset are numeric and can be used with algorithms that don't do well with discrete data, like neural networks or XGBoost. Bam!
In case of linear regression model, all feature values must be numeric. Hence, for categorical variables, we use Boolean encoding for those with 2 unique values and one-hot encoding for those with 3 unique values. One-hot encoding creates 1 new Boolean feature for every unique value of the categorical variable. For this lesson's exercise, check out nonnum.ipynb. This file cleans the data for a grades prediction problem and saves a clean CSV file, which can be used for model training. The link to the repo can be found in the description of this video. To learn more, check out these videos about feature scaling, the different types of encoding, and regularization. In the next lesson, we will tackle classification problems using logistic regression.